All right, let's talk about one of the biggest challenges in AI right now. How do you get an AI to do more than just, answer a single question? Today, we're diving into how to build agents that can actually follow a plan and solve complex, multi-step problems.
So, this is really the big question, isn't it? How do we go from a simple chatbot to an AI that can truly follow a series of steps, remember the whole conversation, and, this is the really crucial part, know when it's stuck and needs to ask a human for help? That's exactly the puzzle we're going to piece together. So the first big thing we need to wrap our heads around is moving beyond just single answers. Modern AI can't just be a glorified Q&A machine anymore. It needs to be a real agent, something that can run an entire process from beginning to end.
And that brings up some major hurdles. For starters, we need these agents to handle tasks with lots of steps, not just one-off questions. They have to remember what you talked about 5 minutes ago. They need to be able to reliably use other tools, like a search engine or a calculator. And, maybe most importantly, they've got to have the sense to say, hey, I need a human to look at this, and be able to pick up right where they left off if something goes wrong.
This is exactly where LangGraph enters the picture. The best way to think about it is as a low-level framework for building these really advanced agents. It's not a prepackaged solution. Instead, it gives developers the core building blocks to create a true blueprint for an agent's entire thought process.
Okay, so to really get this, you have to start thinking like an agent. And what that means is taking a big, complicated task and breaking it down into a simple flowchart of steps. To make this super clear, let's use a customer support agent as our example.
Just look at this simple flow. First, the agent reads an email. Next, it figures out what the email is actually about. Is it a bug report or maybe just a simple question? From there, it might search some docs, draft a reply, and finally, decide if a human needs to give it a once-over. Each one of these is a clear, distinct action. Makes sense, right?
In the world of LangGraph, we call each of these actions a node. A node is really just a function that does one very specific thing. So, read email, that's a node. Draft reply, that's another node. Think of them as the doers or the workhorses of our agent.
And the other piece of the puzzle is the edge. So, if nodes are the actions, then edges are the decisions that connect them. An edge is simply the path that tells the agent which node to go to next. It's literally the arrow in our flowchart telling the agent, okay, you're done classifying the email. Now go search the docs.
So we've got our actions, the nodes, and we've got our decisions, the edges. But how do all these different nodes share information? I mean, how does the draft reply node know what the search docs node found? This brings us to a super important idea, the agent's shared memory, which LangGraph calls state. The state is basically the agent's notebook. It's a shared basket of information that every single node in our graph can read from and write to. When one node learns something new, it jots it down in the state. Then the next node can come along, read that note, and use that information to do its job. This state is really what separates a smart assistant from a simple chatbot that forgets everything you just said.
So, for our customer support agent, this notebook, the state, would hold everything it's learned. It would have the original email content, the classification it came up with, the raw data it found from its search, and of course, the draft reply it wrote. Everything is kept right there, which makes the whole process incredibly transparent and flexible.
Okay, so we've got the core ideas down, nodes, edges, and state. Now, how do you actually build this thing? Well, LangGraph gives you two main ways to go about it, and it really just depends on what you're trying to do. On one hand, you've got the functional API. Think of this as the quick and easy way to get started. You can use standard Python code, like if-else statements, to control the flow. It's great for adding these agent-like features to code you've already written. On the other hand, you have the Graph API. This is a much more structured approach where you explicitly define all your nodes and edges. It takes a little more setup, but its killer feature is that you can actually visualize your agent's entire thought process as a graph. And I just love this quote from the LangGraph documentation because it sums up the whole idea so perfectly. Nodes do the work, edges tell what to do next. It's such a simple but powerful way to think about building these complex systems.
All right, now for the really cool part, the payoff. Why go through all this trouble to define an agent as a graph? Because this architecture unlocks some truly incredible capabilities. Let's just call them agent superpowers. Superpower number one is durable execution. See, LangGraph automatically saves the agent's state, its memory, after every single step. This is called checkpointing, and it means your agent can run for hours or even days. If it crashes for some reason, no problem. It can restart exactly where it left off without redoing any work. For long-running jobs, this is an absolute game changer.
And that checkpointing leads us directly to the second and maybe the most important superpower, human in the loop. You can actually program your agent to hit pause at any critical step and just wait for a human to come in, provide some input, or give it the okay to continue.
And what's amazing is how simple it is to do. Just look at this little bit of code. A developer can just call this interrupt function, passing along whatever information a human might need. The whole agent just pauses, saves its state, and waits for a person to give the green light. It's so elegant.
So, let's pull this all together. Why does any of this matter? Well, it means you can build applications that are truly reliable and don't lose all their progress. It means you can safely bring a human into the loop for those really important decisions. You can create agents that actually have a memory both for the current task and over the long term. And finally, when things go wrong, debugging is so much easier because you have a clear, step-by-step map of everything the agent did.
Which leaves us with one final and pretty powerful question to think about. If you could build an agent that never forgets and always knows when it's time to ask for help, what would you create?